So great. After doing, uh, we want actually right now to simulate or to generate more modes. And why we are doing that? Because we need to know the criteria that we are on which criteria we choose the most suitable node for our next simulation. So actually we generate a lot of modes, so we can stop here and to let us analyze the different modes. For example, if we can take this mode, you know, it's not confined, but the first one is the most confined one. So actually, we will choose this because it's actually uh, achieve the higher effective refractive index with the minimum loss. And actually, there is an article regarding what is group index, what is TE polarization fraction, the waveguide TEM over TM, and the effective area angular loss and whatever. Because where is angular loss? Because actually we do the bend loss, and we will do that later actually. So how can we choose different from different modes? And I actually give you this intuition because you are about to change different parameters. So in which criteria do you choose the most important parameters? So here we choose the first one because actually if you find that the different polarization, for example, 100 TE, it's totally polarized in the electric field, and 0, it's the opposite for the TM mode for the magnetic field. So we will choose actually the first one, the first effective refractive index, and we save 1.4636, the real part for this effective refractive index, and we will put it here in near n. 1.4, but we will choose 1.36. But when we do that, I will tell you right now, we will stop the simulation and try to increase the mesh. Why we do that? Because we need more accurate results. Actually, 120 and 100 by 120. Actually, it's a good mesh, but we can increase it because if you remember from the previous simulation, we use 60 by 60. We can increase it anytime, but actually we cannot over increase this mesh because it will consume your computational resources useless, because you need to compute, you need to efficiently use the computational capability to have the higher accuracy within the suitable time. So you cannot increase a mesh as you want. No, you need to use the most suitable mesh for your design. So great, actually it's suitable. We will not increase the mesh, because actually if we increase the mesh, we will not get very much higher accuracy, accurate results actually. But the difference here, we will use near this effective refractive index. And this effective refractive index come from what? Come from where? Actually from the previous one. Now I will tell the simulation to Muhammad, to compute it around this effective refractive index, right? So again, I measure the structure to assure that everything is okay, calculated properly, and I will calculate the mode. Great. I will do that for the frequency analysis. What is frequency analysis? Okay, you can actually we need, if you remember the paper that I hope you read this, the paper that provided by Dr. Safa here. Yes, optical properties of paper. If you read this paper, you will find a lot of curves. For example, this we simulated this actually, if you focused with me, we simulated this actually, and the paper is generate this results, wavelengths versus effective index, uh, wavelengths versus dispersion, and whatever. How can we generate this curves? You know, how can we generate the data behind these curves? So we will do the frequency analysis. You know, the frequency around, and of course, if you back into our example, you will find how we do that, how we set the parameters. The stop wavelength is 1.4, number of points is 10, number of test modes is 3, and whatever. And of course, you will turn on this track selected mode and the detailed dispersion calculation, because we need to calculate the dispersion itself versus the wavelength and frequency. So again, everything, we can close the bent waveguide here because we didn't analyze it so far. So everything is clear. We will frequency sweep. And actually, we will wait for a minute. Yes. You know, the curve is effective index versus wavelengths. You know, how can we generate this data? If you read the paper, we use it, use the same parameters from, if we use the same parameters from the paper that we need to validate, you will have the same curves. No? Great. So our task here is to try to modify the parameters. For example, use different materials, use different structures, and analyze with the same pipeline. The first one is to specify the materials, specify the structure, specify them as the simulation region, because the simulation region is very important, because if you want to simulate different parts of your device, your sensors, or actually if you have more complicated design, you need to simulate different parts. So within only the simulation region, the simulation is calculate your parameters. No, so it's very important to properly define the simulation region and define the mesh, the confined mesh, and it's very important to use. There is a lot of tips, you know, behind this, because, for example, if you need to analyze behind the core, so I will define a very dense mesh in this specific area, not on all device, you know. So because what? Because we need to consider to efficiently again use our computational resource. We use to get higher accuracy, higher accurate results with the minimum amount of time, right? So again, you will do the same steps, but with different parameters and different structures based on the physical properties of what you are about to design, the engineering behind this parameters. Why you manipulate this? Why you change it from circular to square? Why you use this materials? Is the use the right equation to model this material or not? So great, we are about to finish. Great, here we go. So this is actually the curve. We can, yes, if actually the effective index versus wavelengths, like what we get in the paper, no? You remember the paper? Yes, wavelengths versus effective index. But here he used different range from 1 micrometer to 1.9. No, so we can do that again. You can use different range and different, of course, effective index range in the subsequent results. So he is effective index versus wavelengths, but we can not only effective index, we can use the loss versus wavelengths. We can use the gain, can use groove velocity, we can use dispersion, we can use beta, what you want. So of course, it's very important to, if you are about to write a paper or whatever, you take this, the image of those paper, but actually you can use more points to generate more data. So how actually you extract this data? We go from here, data export, and we can export the data from here. It's very important because frequency data, we can use frequencies, yes, and again we can see this. Here is our data. Great. So it's very important to note what we are about to create. No? So actually we finish our very basic photonic crystal fiber. So now you can modify and you can use different parameters and different structure and use, for example, if we can use, let us experiment, test a very trivial thing, because if we are about to change the fiber material, actually we can use any other material. For example, we can use whatever, silicon nitride, yeah, anything, anything, only to test what is the difference between using these parameters and using this material. Of course, to use different you notice a change when we mesh the structure, and we can calculate the moves. No, so of course, if you use different materials, you can generate different data, and you need to manipulate the subsequent parameters to get the most accurate and the most efficient and the most optimum results for your design. So actually, it's a very it's a very arbitrary results, because there is no confined mode here, so there is nothing to study. So actually, I use this only to show you the difference between the first material and this second arbitrary material. Any material, actually, you cannot do this by mistake. But I only show you this only for educational purpose. I only show you what the difference between this material and whatever. So if everything you need to modify and change, you need to have the physical concept and the physical background, physical equation behind it, right? So that's it. Thank you. See you again.